Hey, pre-calc. So here's our do now. Our graph walker Azul is going for a walk, feeling down in the dumps. We're going to try to commiserate by identifying the coordinates of the physical low points on Azul's walk. Maybe more than one. Identify all of the low points as Azul walks across the graph from left to right. Go ahead and hit pause on the video so you've got those identified. All right, so there are 3 of them that we're looking for. And I didn't exactly specify, but we're thinking like if you describe this in terms of hills and valleys, and like you think of the graph as like a landscape, we're looking for valley points. So -8, -4 here in blue, 0, 0 in green, 5, 0 in magenta. All right, today, continue our journey through the intro to calculus and its some of its notations. With this learning target, you'll be able to describe a graph using relative and absolute, maxima and minima. All right, so relative and absolute, those are like the adjectives. The things we're looking at are maximum points or high points and minimum points or low points. And there are some different kinds. Not all low points are created equally, like we just saw on the do now. The blue one is lower than the green or the magenta points. And so it's useful for us not to just be able to identify where low points are, but to be able to say, look, this one is like the lowest point. Right? And so that's what an absolute minimum or an absolute maximum refers to. All right. Well, here are basically all of the notes in picture form for today. So there's a variety of different types of points that we're going to be identifying. We'll describe them in the picture going from top to bottom. So the absolute maximum refers to the very highest point anywhere on the entire graph, right? And so the highest of the hilltops. Okay. For each of these points, we're going to identify it using coordinates, just like you saw in the do now. So this one, nothing is labeled, so I can't give example coordinates, but I would give the coordinates for this point. That's the absolute maximum. Okay, slightly lower than that is this other hilltop, just over here to the left a little bit. So I'd call that a local maximum. It still clearly looks like a hilltop, but it's not as tall, right? Local refers to like this little local area of the graph, and you can define this little local area of the graph in kind of whatever is convenient. So you could say, what's the highest hill like on my block? Like which house is the highest on my block? Or we could say, well, gosh, what's the highest hill in Mount Lake Terrace? What's the tallest mountain in Snohomish County? What's the tallest mountain in Washington State? And then what's the highest point on the planet would be the absolute maximum, right? So local can be kind of described in different ways, but some things need to stay in common. We can't like describe an infinitely small location of the graph and say, well, this little tiny point right here, when it's, just like the side of a hill halfway up or something, right? That's not helpful. So if somehow this graph walker were able to step one step to the left or one step to the right, when they do so, at a maximum point, they would go lower when they step to the left. Also, they would go lower when they step to the right. That's how I know it's a maximum point. Okay. Next up, minimum. So I got a local minimum here labeled with the green words. Local minimum point is like a valley point. In this case, it's between 2 hills. It doesn't have to be between 2 hills. Maybe it's the bottom of a parabola and there's not actually hills. It just, both arms of the parabola go up. Okay, so to identify a minimum point, again, if the graph walker were able somehow to step either left or right, when they do so at a minimum point, they need to be higher when they step either left or right. And so in this case, my little graph walker is going to go to the left. That's a little bit higher. And if they go to the right, that's a little bit higher. So that means this is a minimum. All right, lastly is the absolute minimum. And this graph should actually have some arrows drawn on here. It does continue forever. Somehow those disappeared. So the absolute minimum on this graph is, in fact, infinite. And some graphs, many graphs maybe have infinite features. Not all graphs have infinite features. This one goes down infinitely far. And so if we were asked to describe the absolute minimum, we would not be able to give coordinates because I don't actually know where that happens. It just keeps going and going and going, and is like further down and further down and further down. I can't give coordinates for that. I don't know where it ends because it doesn't end. So the infinite feature of the graph would just say, look, the absolute minimum is infinitely far down. So we just say negative infinity. And we don't have to specify that it happened at the right end of the graph or the left end of the graph. In this case, it's at both ends. They're infinitely far down, right? But if you can use coordinates, use coordinates. If it's infinite, then you say infinite. So negative infinity for down infinitely far. If the graph were upside down, then all the maximums would be minimums, the minimums would be maximums. And in that case, the absolute maximum would be positive infinity, infinitely high up. All right, let's take a look at this graph from the do now. So we're going to look at 4 different questions, and we'll go back and we'll see them on the graph. So let's just do one at a time. Not all graphs are going to have all of these features, but here's the 4 questions I'm going to pose to you. So first, absolute maximum. All right, well, on this graph, it's going to be infinitely high. All right, we're going to be careful because the way the graph is drawn, 210 looks like the highest point that has been drawn, but we know that the arrows mean that it actually continues even higher. It's just not drawn that way. So positive infinity is going to go up infinitely high. Absolute minimum, well, the lowest it ever goes is at this point right here, -8, -4. And any local maxima, so I'm looking for any kind of hilltops, and there's 2 of them right here, -2, 6, positive 2, 10. See if I can remember those long enough. See if I can write those down by memory. Okay, so on WAMAP, we're going to have to give, if there's more than one point, we have to give them as a list. So I need to have a comma between those 2 coordinates. And also make the commas look like commas. Lastly, any local minima. All right, well, so -8, -4 is a minimum point. I've already used that. I've identified that as the absolute minimum. So I'm not going to repeat it. I'm looking for other points. So there are these other 2 like valley points, 0, 0, and 5, 0. All right. So here are the answers we came up with. There they are on the graph. Okay, just real briefly, let's look through some other examples. So I've already written these out so we can just see the answers and identify what that looks like on the graph. Same 4 questions. So absolute maximum, in this case, at 5, 5. It doesn't go any higher than that. Absolute minimum, infinitely far down, so negative infinity. Local maxima, there's one other maximum point here at -1, 4, and local minima at 2, 2. So that's like the valley point between the 2 hills. All right. On this graph, absolute maximum, infinitely high at positive infinity. Absolute minimum, infinitely far down in blue there, negative infinity. Local maxima, there's just that 1 right here at 1, 5. And local minima at 5, 1 down here in red is the off to the side. There's kind of a valley. What about those yellow points? I didn't write those down anywhere. They're labeled as points. I've got them highlighted. There's clearly something important happening there at -1, 3 and at 3, 3. Those are not maximum or minimum points. Something important is happening. They're totally labeled. When you get to calculus, those are going to be more important as an inflection point where the rate of change, if we think about the slope, how the slope is changing, it goes from steeper slope to less steep and then back to steeper again. Okay, not relevant to anything we're doing right now. They will be definitely important later. So if you have points labeled on the graph that are like you're confused about, don't think that just because a point is labeled, you have to include it someplace, right? If you're not sure, use your little graph walker. If I put a little graph walker on this point, and I think to myself, I think that's some kind of maximum. Well, if it's a maximum point, my little graph walker is going to break the rules and go one step left and one step right. When they go one step left and one step right, if it's a maximum, they need to be lower both times. If it were a minimum point, if they step left and right, both times they should be higher. And in this case, if I step to the left, it's lower, but if I step to the right, it's higher, right? So that's not a maximum or a minimum point. Same thing over here, right? So graph walkers are your friends. Use them to help figure things out. All right, another one. Absolute maximum, infinitely high, positive infinity. Absolute minimum is negative infinity. Local maxima, there are two of them at 1, 6, and 5, 4. I should have a comma between them. So this graph is interesting maybe for a couple of reasons. First, there's a discontinuity, right? So at 1, 6, the graph is discontinuous. It's got a jump. That's okay. We can have a point where there is a discontinuity still be either a maximum or a minimum. In this case, it's a maximum. Okay, think about our little graph walker. If our little graph walker is standing on that point and they go one step left, one step right, if they go left, that's lower. If they go right, also lower. They're going to just follow where the graph is. That's the first rule of graph walkers. Always they walk on the graph. So if the graph is discontinuous, they just magically reappear at the next spot where the graph is. It's lower. So this is an absolute maximum, or sorry, is a relative or a local maximum. Okay, this yellow point, on the other hand, sorry, I'll show you the local minima down there at -1, 1 and 3, 1 in blue. So the other interesting point happens at the yellow point. The yellow point, first of all, doesn't exist, right? It's an open circle. If there's not an actual point there, you can't use it for anything because the point doesn't exist. So we only use points that actually exist. So sometimes people say, well, what about like the point right next to it? That'd be like some kind of local maximum, right? Well, yeah, maybe it would, but the convention says we don't give the coordinates of points that are like right next to an open circle because it's just not the way it's done. All right, so if there's an open circle, it's not ever going to count for anything. And you don't need to worry about finding out, well, what are the coordinates right next to it? We don't do that. Okay, what if the graph were different? What if this had been a closed circle? Would it be a maximum or a minimum in that case? The answer is still no. So we can use our little graph walker to figure this out. If you put the graph walker on that yellow point right there, step either left or right, what happens? Okay, if you go to the right, that's lower. If you step to the right, graph walker magically teleports up to this next point. That's higher. Well, if one's higher and one is lower, it's not a maximum, it's not a minimum. It's an interesting point, but we don't list it for either a maximum or a minimum.